Today we're learning trig sub. Let's start off talking about why you even use trig sub in the first place. Sometimes you're gonna think, oh, I'll use U substitution. Oh, you can't. Or, oh, I'm gonna use integration by parts. Not gonna work. Well, that's where trig sub comes into play. It's a little trick to use for integrals where they fit this form and you don't know how to integrate them. So if you have an integral and there's a radical within that integral where you have a constant, and u a function of x or whatever variable it is, and it looks like you have a squared minus u squared, a squared plus u squared, or u squared minus a squared, you're gonna be able to use trig substitution. You're gonna be able to, within that radical, exchange the u value for a sine theta. I know this sounds confusing, it kinda is. This is definitely one of the more difficult integration techniques, but let's just do an example. I think you'll start to catch on. So let's say you have the integral of dx over x squared times root 9 minus x squared. So let's rewrite this as the integral of dx over x squared times root 3 squared minus x squared.
Really quick, just to clarify, if you see a radical in the numerator denominator anywhere in the problem, if it fits the trig sub form, you can use the trig sub rules to solve the integral if you think it's helpful. It doesn't matter where that radical is. Okay, back to the video.
So if we compare it to our formula over here, our a value, a equals 3, and our u value equals x. So what do the trig sub rules tell us? We're gonna let u equal a sine theta. So since our u is x, we'll say let x equal 3 sine theta. That means our dx equals 3 cos theta. So if we rewrite our integral, we have 3 cos theta over x squared, so 9 sine squared theta times root 9 minus 3 sine theta squared. So now we're gonna simplify this radical, and after we do that, you're gonna see the whole reason we do trig sub, because this integral is going to become manageable. So I'm gonna do it over here, a little side work. So we have root 9 minus 3 sine theta squared, which is equal to 9 minus 9 sine squared theta. Now we're gonna factor out a 9. So we have 9 times 1 minus sine squared theta. We can pull the 9 out of this radical, so we have 3 times 1 minus sine squared theta. If you remember your trig identities, 1 minus sine squared theta is cosine squared theta. So we have 3 times root cos squared theta. Square root of cosine squared theta is just cosine, so we have 3 cosine theta.
Are we supposed to memorize our trig identities?
Josh, every video you ask me some stupid ass fucking question. Of course you have to memorize it. All right, so now that we've simplified this radical, let's rewrite our integral. So we have the integral of 3 cosine theta over 9 sine squared theta times 3 cos theta. Well, looky here. This is gonna cancel with this, and we're left with the integral of 1 over 9 sine squared theta. All right, so let's pull out this 1 over 9. We're left with the integral of 1 over sine squared theta. Stop yourself. What is 1 over sine squared equal to? This is equal to 1 over 9 times the integral of cosecant squared theta, because remember 1 over sine is equal to cosecant. Now just from our trig integration rules, we know that the integral of cosecant squared is negative cotangent theta. We have that times 1 over 9. Now you might think we're done, but we're not. So this was the original problem we had. It was given to us in terms of x. We cannot give an answer in terms of theta. We have to rewrite this in terms of x. So this is where a lot of people get tripped up. So remember, we set x equal to 3 sine theta. We're gonna use that information to replace the theta in our answer here. We divide both sides by 3 and we get sine theta equals x over 3. So now we're gonna go back all the way back to pre-calc and get this, draw a triangle. So remember your SOHCAHTOA. Sine is opposite over hypotenuse. We have the opposite and we have the hypotenuse here. So we have x, 3. We need to solve for this value down here, and we can just use Pythagorean's theorem. So a squared plus b squared equals c squared. Our a, this is our a value here, we don't know that. So a squared plus b squared, which is x squared equals 3 squared, which is 9. We're gonna solve for a. So a squared equals 9 minus x squared. A equals root 9 minus x squared. Oh my gosh, this is the same thing we have up here. I can't think of a time when it hasn't been the radical from the original problem. I don't want to say that's always what it is, but this is basically what it's like. If you had to guess on a test, like I can't solve for this, it's almost always this.
What if this doesn't equal that?
That's okay. That's totally okay. If you know you did your Pythagorean theorem correct, it doesn't matter that this doesn't equal this. I was just trying to make the point that most of the time in the homework problems I've done, it's been equal to the radical from the original problem. So now our new triangle looks like this. We have x, we have 3, and we have root 9 minus x squared. Now all we have to do is look back at our SOHCAHTOA here, right? So if tangent is opposite over adjacent, cotangent is adjacent over opposite. So here's our adjacent, here's our opposite. Let's fill those values back in here. So we have 1 over 9 times, once again, adjacent over opposite. Adjacent, root 9 minus x squared. I'm sorry, there was a negative here from up here. Over opposite, x. And we multiply the 9 in and we get negative root 9 minus x squared over 9x. Oh shit, motherfuck! Plus c. I swear to God, I forget plus c and dx more than any of you. And I am just I'm so underqualified, Josh, really. Well, thanks for watching this video. If you like it, you don't have to like it, but just leave a tweet or a comment or something for my math BFF. And just tell her that, like, I'm looking to be friends and, like, maybe even more than friends. And, like, not in a creepy way, just like a way that's like, I'd like to take you to a nice restaurant. I'd like to get to know you better, not just because we both do math, but because I think as a person, you're a kind-hearted spirit, and you're somebody who I could see starting a family with and moving, you know, to somewhere in maybe Ottawa to just work on functions and algorithms and developing new ideas.